Right, welcome back everyone. I hope you've had a chance to have a beer. Looks like the pizzas were relatively popular tonight because we've completely cleared those out, which sometimes we get left over, so that's a good thing. Anyway, so I'd just like you all to give Hooman a great welcome to the stage, and he's going to tell us everything you want to know about HTTP2 and like what is kind of happening, especially in light of the question that came in the first half about server push. Right.
Yeah.
Anyway, please give a nice welcome for Hooman.
Please, 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 please. Hi. It's hard enough to follow the greatness that is in Andrew Best's presentation, but in Andrew Best's presentation and pizza, this is rough. If you fall asleep, I don't mind. I only had 3 hours of sleep last night, so if I fall asleep, please also do not mind. I'm going to talk to you about H2. I have a lot to tell you, and this is a dense presentation, so apologies in advance. And again, if you fall asleep, that's fine. Let's start with a couple of questions just so I get a feel for where you're all at. How many people know about H2? Nice. How many people are using H2? How many of you could come up here and do a 5-minute presentation on H2?
2.5.
Nice. It's not bad. I'll take it. And how many of you were at last month's meetup? Was it last month? We had a panel
at the end of April.
End of April,
yeah,
where we talked about HTTP and Quick and things like this. Okay, great. Let's talk about HTTP2. I'm going to go kind of fast. There'll be places where I'll stop and we can have questions and answers, but we're going to try to get all the questions at the end because there's a lot of stuff I got to tell you. RFC 7540 was ratified now over 2-3 years ago, and that's where HTTP2 was defined. It is now being basically supported by most browsers, if not all the important ones. So all the clients have support for it. Anything that's server or like looks like a server pretty much has support for it. You'll see that there's a lot of green there. And anything that looks like a server but cloudy, so like CDNs and ELBs and XLBs, generally have support for H2. But there's a question about adoption. Now, we did this really scientific study a minute ago about adoption in this room. I haven't actually seen research about adoption in the wild, but I work at Fastly and I have access to a network that's taking a lot of requests. So I can look at the traffic. So before I show you the data, and in our case, H2 is an opt-in service, which I like because it lets me look at adoption over time. I'm going to show you a graph over the entirety of 2017. If you had to guess, out of that many requests per second, what % do you think is currently H2? If you had to guess, just throw some numbers out. 7%. 7 requests, that's really low. It's roughly 40%. That's where you see the growth over the time. Now, this ends in 2017. I looked at it again this morning. It's right around 41, 42% of the requests. Again, we're opt-in service for now. So a couple of years ago, about a year and a half ago, because I'm a student of protocols, I decided to study the protocol and put some of its claims to test, if you will. So I did a bunch of stuff. I did a bunch of tests. I ran a whole bunch of, I gathered a bunch of data. I put slides together. Very proudly, I took this on the road with my head held high. And I talked about H2 in the wild. You guys, you know who this is? You know the tick? That's right. I like you people. Unfortunately, that link is not for this magnificent walk. It's for the presentation that had some of this data that I'm talking about. So what I thought I would do about a year and a half later was to come back to the core principles of H2 and put some of the things that we sort of discussed a year and a half ago back to test and see if there's been anything new and sort of talk about, basically do an update. But what I'm going to do is I'm going to start with some core concepts. I'll go through how the protocol works. A lot of you raise your hand, so I'll go through that rather quickly. I'll talk about its major features. Like in this case, I'll highlight 4. And then as I go through them, I'll talk about if anything's changed, if there's an update, if we should ask Patrick any more about what features are working or aren't working. And what's happening next. So let's start with the basics of H2. As you may already know, gone is the text-based protocol that we know is HTTP1, and HTTP2 is a binary protocol where everything lives basically on top of a single connection. That connection is made between a client and a server. It's a long-lasting connection, and theoretically, this is good for the state of the internet because this creates a single congestion context, and that's good for the server and the client performance-wise, because TCP is known as basically not having awareness about what neighboring TCP connections are doing. So the premise here is that if you put everything on a single connection, things are going to get better. It uses TLS. The spec itself doesn't mandate TLS support, but all browsers basically forced their hands and said, we're only going to do the TLS version. So they use the ALPN extension of TLS, and every H2, mostly every H2 request that you're going to see in the wild is going to be a TLS request. Inside this single connection, there are these virtual channels called streams. Clients and servers communicate over these streams. Again, these are virtual communication channels, and they translate, a stream translates roughly to a single request and response exchange between the client and the server. The cool thing about streams is that either side can initiate a stream. And every stream has a stream ID, and the odd ones are client initiated, the even ones are server initiated, 0 is reserved. And the only requirements are that each stream ID needs to be bigger than the one before it, and you can't reuse stream IDs. Now there's 2 to the 31st, 2 to the 31 is the total number of streams you can have. You divide that by half for each of the client side and server side. That's a lot of streams that you can essentially have in a lifetime of a connection. Every stream is stateful, and it even has a state machine, a state diagram. That's the state diagram. I'm going to spend the next 15 minutes going into each of these boxes in great detail because I'm kidding, of course, please. The smallest unit of communication in the world of H2 is something called a frame. And every frame that goes back and forth between a client and a server carries the stream ID. This is why the streams are virtual communication channels. And basically all communication between the client and the server is through frames. As you can see, not just from the state diagram before, but from basically where we're headed, HTTP is no longer really a stateless protocol, which is something we liked about HTTP1. But for the advancement of the interwebs, we have now got ourselves a stateful protocol. So what used to look like this, a simple text-based request in the HTTP1 world, where the client sent a request and a bunch of headers, and the server responded with a bunch of response headers and a bunch of data, now turns into the client sending a headers frame to the server that carries the request, and the server responding with a headers frame that carries all the response headers, and then a whole bunch of data frames that carry the data itself. So everything that we do in HTTP2 is essentially frame-based. Everything comes across, all communication happens in a frame. The spec defines 10 frame types. I'm not going to go through all of these. But I will tell you that the idea of the spec is for this to be extensible. So already there are 11th and 12th and 13th and 14th frame types that have been defined. If you were to look at any client and server talking and were to inspect the wire with some tool, you would basically see these 3 frames the most. You'd see header frames, and you'd see data frames, and you'll see some setting frames. And setting frames essentially dictate meta information about that connection context between the client and the server. If you like pretty pictures, this is what the HTTP1 sort of stack looked like before. You had TCP with TLS on top of it or inside of it, or however we look at it, and everything in TLS is transmitted through TLS records. In HTTP2, it kind of looks like this, where everything inside the TLS record is HTTP2 frames, and then all the communication is happening inside those frames. When you look at it like this, it's easy to understand why there's a fair argument about how HTTP2 is actually a transport protocol for HTTP rather than a brand new protocol on its own. And I think this is probably a good way to visualize it. So what's the protocol flow look like? Well, in the past, in HTTP1, you had a connection between a client and a server. The client sent a request, and the server sent a response back over that connection. In the new world, the client sends a headers frame that carry all the headers for the request, and the server in response sends a headers frame that has all the response headers and a bunch of data frames that has the payload. In the past, though, when we had HTTP 1, while that request was going to the server and the response was coming back from the server, there was nothing else we could do over this connection. This caused a phenomena that we call header line blocking. Essentially, the idea is that while this request to respond is in flight, this connection can't be used for anything else. And that is what we call header line blocking. How did we get over this in HTTP 1? Well, we opened a bunch of connections. So we opened multiple connections. Browsers got to a point where they're opening 6 per domain, and we thought we were clever by sharding. So we opened 6 more per every new domain, so we could have a lot of parallelism happening. In H2, we don't have to worry about this anymore because we're free to send headers frames and data frames as we please. They flow back and forth freely between the client and the server. This essentially gives us 2 of the biggest features of HTTP 2, which are multiplexing and interleaving. Multiplexing because we're allowed to do lots of things at once, and interleaving because we're interleaving the data that's going back and forth. So we can send a data frame from stream 1, and then a data frame from stream 3, and then another data frame from stream 1. This is a thing that we couldn't do in the past with HTTP 1. Somebody thought it would be cute to create this analogy for HTTP 2 and HTTP 1. It is cute and delicious. If you like looking at waterfalls, which every one of you I'm sure does, this is what an HTTP 1 waterfall looks like. This is what an HTTP 2 waterfall looks like. You'll see lots of things happening at once, a lot. This is the concurrency, multiplexing, and interleaving that we know and love in H2. And if you were to have a tool, let's say Wireshark, and you were going to look at the frames on the wire, this is what it would look like. And yes, Andy, my color filter for H2 is peach puke. I'm open to new suggestions. Okay, that's a crash course on H2. For the 3 people that didn't raise your hands before, and you're now experts, you can get up here and do 2.5-minute talks of your own with Perry as you tag team. Okay, so let's talk about H2 and this context of TCP. And the biggest promise of H2, arguably the biggest feature that was touted as the protocol was coming to fruition, was performance. And the idea was that when we have a single connection context, we do all this multiplexing and interleaving, we're going to have a better performance profile between a client and a server. So I decided to put this to test. Should be relatively easy to test, right? We have tools. We put some things on a page and we run it with H1 and H2. We'll see. Things will be great. So I made this test page. What I picked was basically the best case scenario for H2, which was a very simple page with just 100 images on it. They're all 10K images. It's just the same image over and over again, just named differently. The waterfall for that page in H1 looked like the waterfall on the left. For H2 looked like the waterfall on the right. This is kind of a best case scenario. Get 100 10K objects from server to client, and interleave them and do whatever you want to do in the world of H2. And this should be a good performance test for the protocol. The mistake I made here was that I chose this image as the image for to repeat on the page, which was really cool the first like 3 times I did this. Unfortunately, I did this test hundreds and hundreds and hundreds of times. So this was nightmare inducing after a while. I already have triggers just looking at it. What makes this worse is that I did this talk a few times, and every video that was published, that was the thumbnail that they chose. So there's a very cruel asshole somewhere. Sorry, there's a very cool asshole somewhere that thinks this is funny. That's great. That's great. So there we go. There.
Noted.
You also don't have. I hope you don't have the same nightmares that I did. So I did this. Now we have tools at our disposal, and we all like web page tests. So I decided to use web page test. So I grabbed a standard bandwidth and latency profile, 5 megs down, 1 meg up, 40 milliseconds of latency. Use Chrome, and then the idea was to compare H1 to H2, and I ran lots and lots of different tests. The reason I liked web page test is because it had this one extra feature, and it's the fact that you can basically define your own connection profile. So not just download speed and upload speed and latency, but also packet loss. And the world has packet loss. So it'd be really interesting to see how the single connection context reacted to packet loss. So that's the thing I really wanted to play with. And that I love web page test anyway, but the fact that it gave me this feature made this even more appealing. So under that profile of 5 meg down, 1 meg up, 40 milliseconds, I tested with 0% packet loss, 0.5% packet loss, 1% packet loss, and 2% packet loss. So this is a scatter plot of the results with Chrome, H1 versus H2 with 0% packet loss. Blue is H2, orange is H1. Okay, that's cool. And then let's add packet loss. Here's with 0.5% packet loss, 1% packet loss, and 2% packet loss. And all of a sudden, a picture starts to form that is not necessarily flattering for this new protocol. Okay, is this a Chrome thing? Let's try it with Firefox. And this is what it looks like with Firefox. Kind of the same. Now, it's true that the bottom right is disappointing, but to be honest with you, I'm only semi-whelmed with the upper left, or I was at the time. That's a good, yes, H2 is faster, slightly more consistent, but is it game-changing? This was the question I really wanted to answer. Okay, that's fine. 5 megs of bandwidth is a lot of bandwidth. What if it was like low bandwidth, bad performing bandwidth profiles? So I tested with something that was pretty crappy downlink, pretty crappy uplink, pretty crappy latency. Again, the same thing with packet loss induced. And the picture was slightly different. Only in that when there's no packet loss, H2 did show better performance. And that's noticeable. I can buy what's happening on the upper left there. What's happening in the lower right, I'm not super keen on it. I decided that this was interesting, so I made a little scorecard with some core performance metrics at the time, like dot complete, DOM content loaded, and speed index, and compared with 0 and 2% packet loss Chrome and Firefox against the different bandwidth profiles. And I was doing this like weird page with 100 creepy objects on it. What if I tested some realistic sites? And I did that too. And then there's this big sort of report card that I had in this presentation. Considering the scatter plots that we saw, I think the right half of this is somewhat expected. But again, I really was expecting more greens on the left half of this. So that was, slightly disappointing, especially considering the buildup to how great this protocol was going to be. I'm not necessarily saying this is a bad thing. I'm just saying, lessons learned. And we are here to discuss lessons and revisit those lessons. Why is all this happening? Well, it's happening because this analogy is actually inaccurate. This is not really the way you should compare H2 and H1. This is actually a better comparison of the two protocols, because what was happening is, yeah, we can do more things over a single connection, but H1 allowed us to have multiple parallel connections doing things at once. Now look at what happens to a TCP connection. And for the time being, when I say TCP, I mean standard default TCP on the interwebs, which uses a congestion control algorithm known as Hvac, if you haven't heard about this. This is how standard default Hvac behaves. There's a ramp up period, and then basically TCP tries to get itself to a point where it's converged at an optimal bandwidth. What you see here is time on the x-axis and the number of bytes that the server thinks it can send at any given time without being acknowledged on the y-axis. Now look at what happens to this when there's packet loss. Hvac works under the assumption that packet loss means there is a congestion event or a problem on the internet. So what it does is it drastically reduces the number of bytes that it's comfortable sending out without an acknowledgement. And you keep shoving these packet losses into the wire, you get a drastic change in the number of bytes that the server is willing to send. What this is essentially showing is that it's true that with H2, we removed the header line blocking that was in HTTP inherently. But what we've done is we've actually exposed header line blocking in TCP. And look at what happens if I have 6 concurrent connections happening at once, all being subjected to packet loss. If I take the sum of their CWINs, the number of bytes they can send at any given time, the sum is greater than any single one of them. And this is probably the reason that some of the H1 tests were doing better than H2. This isn't necessarily a revolutionary find. This was a known issue. In fact, if you've read Ilya's book, which I highly recommend, this won't be the first time I'll talk about it, he mentions it. Actually, the people who wrote the spec also talk about it, that this has now exposed header line blocking in TCP. I think at the time, and maybe still, my issue with it is that if loss is causing this much of a problem. In the panel that we had here a month and a half ago, one of the panelists said H2 performs really well until there's loss. Well, there's loss. Loss is a thing that we always have. And I'm not saying that the design of the protocol was to be in a perfectly lossless, clean, and sterile environment. But this is a lesson that we're learning as we're going through deployments, that this loss could have an adverse effect on the protocol. Here's a bunch of reading. I'll make these slides available afterwards. Again, I was not the first person to find this. Others had essentially exposed similar things. There's some reading about it. And at the time, the takeaway was that there's some, first of all, just to be clear, the experiment itself was flawed. The experiment was flawed because it was a very simulated environment. This was not a real world environment. It was an environment where we gave the client and the server adequate bandwidth, but we injected packet loss into the network. We simulated packet loss in the network. It's a synthetic packet loss, and that's not really the way it happens in the world. It's close. I think it tells us what the protocol does when there's packet loss, but it's not necessarily a direct reflection of what happens in the world. But despite the flaws with the experiment, the performance benefits themselves were slightly less than clear-cut. Certainly not if you were like me and went to these H2 presentations 3 years ago and came out of it with pom-poms and flags and waving T-shirts around. You probably would have been slightly disappointed. But there was enough evidence out in the world where people had tried it and saw benefits. So I think the lesson for me, the biggest lesson for me was, don't listen to anything anybody says. That included me. I made sure that people specifically didn't listen to me. And this was a thing that it's best tried on your own. This would be a good thing. There is a certain situation that H2 is going to be good for. There's going to be certain situations that it's not going to be good for. And the best thing is to actually try it out. And we always say this in the performance community, A/B testing and trying things out and collecting data and making decisions based on data is really the right way to handle things. Now, that was then. Has anything changed? If you take this data today and go to somebody, go to 100 people and say, okay, what do we do about this? How is the world different? Is there anything we can do? How can we solve this problem? You're going to get one of 5 different answers. Okay, the first one is going to be, I don't know. That's going to be the most likely answer, is just a shrug. The second likely answer to what the hell do we do about this is nothing. That's the answer. This is what we designed. This is what H2 is doing. We don't do anything. It's still it's still as a protocol, it's a better protocol. It's a better network citizen. We don't do anything. The third, and really funny to me, maybe not funny to you, was I heard recently from, I think it was a CDN, I'm not sure which CDN, that said, hey, why don't we shard with H2? Let's shard connections with H2. This is funny because one of the reasons that we want the single connection context is to get away from sharding. So I don't know if this is true. This was third-person information that I got. Somebody overheard somebody. I kind of hope it's not true, but there's a little bit of me that kind of hopes it's true because it'd be really funny. When we write the history books, it'd be really funny. The fourth thing you're going to hear, I'm not going to tell you about yet. The fifth thing you're going to hear is this thing called BBR. BBR is a new, I think it's fair to still call it experimental, congestion avoidance algorithm developed out of Google. And the idea of BBR is listen, I'll just say this right now. Congestion avoidance algorithms are a science. Every time I've tried to have somebody sit me down and explain these things to me, I come away dumber than I started. There's a reason these are 4-year dissertations. Like, this is a complex art, if you will. But what I'll tell you is some very basic things about it and just inform you of it. So BBR is this new congestion avoidance algorithm. The basic premise of BBR in this video that Google so kindly provides for me to steal is that Hvac takes packet loss as an indication of congestion. And BBR works completely differently. Packet loss doesn't necessarily mean there's a congestion in the network. What BBR does is it constantly measures round trip and packet sent, bytes sent, to measure bandwidth. And it tries to optimize for best bandwidth, not necessarily packet loss. So a packet loss event doesn't necessarily mean there was a problem on the network, which is why with BBR, you'll see a lot more retransmits on the wire. It's much more aggressive. That'll come back in a second. That's the basic premise of BBR. It's an experimental protocol. I believe it's shipped in kernel 4.9. There's a whole bunch of reading. If you like reading scientific things, these are extremely scientific and very cool. And that's right, I can do those things too up there. Some people exchanged some, released some data on it. Netflix had this thing that they released where they did some video streaming with BBR and without BBR, and the results were generally positive. Dropbox also had a study they ran that they published where basically general throughput was higher with BBR than it was with Hvac. I did some tests because I don't believe anyone ever. So what I don't have necessarily the network that Netflix has. I have the network. I don't have the control and the client side that Netflix has. So I did some tests with this tool called Catchpoint. Many people know Catchpoint. Basically a synthetic testing tool with a lot of test nodes deployed in people's homes. This is what I like about it. So these are relatively realistic connections because they're sitting by somebody's microwave behind somebody's router. I downloaded 1 meg objects across, I don't know, each of these, each pair of lines is a single location. It's 300 to 600 requests per location. Shorter lines are better. It's load time. You'll see that this is the median across those 300 to 600 requests. It's a mixed bag. There are times that BBR does better. There's a couple of times that Hvac does better. At the 95th percentile, it's slightly different. You'll see then when it's good, it's really good. When it's bad, it's really bad. What's the takeaway about this whole BBR spiel? Some things to know. There's an open question as to whether BBR is a good network citizen. Somebody called it network waterboarding, which is funny, just visually, that's a funny notion. I think all the people that worked on BBR and are working on BBR kind of acknowledge that there's still work to do. One of the authors of BBR is at Fastly, so we've talked about this a lot. The fact that there isn't enough data yet is acknowledged. We need the data to basically figure out if this is a good path for us forward. So again, as usual, this is a call to arms. If you have a way to test Hvac versus BBR, the data is going to be valuable for the rest of the world. I'm not sure about other CDNs, but at Fastly, we allow you to turn it on. You can turn it on through your configuration, and hopefully you have ways to collect data. I will say that my personal opinion is I'm warming up to BBR more and more. The most of the data that I see is positive. There is some iffy stuff out there. So I actually want more data before I can declare a winner. I don't know if I'll ever do that or anybody should ever do that. But the lesson again is get it to be available to you. Ask your vendors or your servers or your network people to try it out and see if what you find is beneficial. And if your data is good data, release it back out to the world so we can learn. That's TCP and that's performance, but that's not where our story of TCP and H2 ends. H2 also introduced this feature called coalescing. And the idea was that you can have requests across multiple domains actually flowing over the same TCP connection. They called it connection reuse, and specifically the rule was that if the two host names resolved to the same IP address and they sat on the same certificate, you can coalesce those requests across a single TCP connection. So you can take A.com and B.com and put them on the same connection if they both lived on the same certificate and they both resolved to the same IP address through DNS. You would think that's pretty simple. Those are pretty simple rules. But as with any RFC, there is a lot of interpretation in those two seemingly simple sentences. So I encourage you to read this blog post from Daniel Stenberg of Mozilla and curl fame about how coalescing is done in Firefox because it is slightly aggressive, and that's being slightly kind. What it'll do is, and read this for more details, what it'll basically do is it'll take as a signal that two host names are eligible for coalescing if at any time during the lifetime of this browser, any DNS lookup has shown an overlap. So if you're trying to do fancy load balancing or A/B testing, sometimes you'll end up getting requests on a connection that you never expected to get. This is just something to be aware of. This blog post is a very good reference to know exactly what's happening, and you can come up with mitigation techniques from there. But I have multiple scenarios where customers have come to us and said, we saw a request on a connection we weren't expecting, what's happening? And it's usually traced back to something in the coalescing code of a browser. Now, H2 provided us a new response code of 421 to fight this. And a 421 essentially says, the request that you've sent me, it does not belong on this connection. It's, what is it, a misdirected request. It is at a cost of a round trip, because that's how long it'll take. But there is a mitigation technique within the protocol. This isn't necessarily the best way to do it. It is a way to do it. It's not necessarily the best way because not necessarily all the browsers support it very well. In fact, I remember there was a bug. One of the browsers would handle this very poorly. I think it's been fixed, but still, as with any new technology, there's kinks. So enter, and this is new, RFC 8336. A new HTTP2 frame known as the origin frame. The origin frame's idea is to essentially give coalescing control back to the operator, that being you. So there's a number of things you can do with the origin frame. If you don't send it, the origin frame essentially, what the client will do is default to 7540 rules, which is coalesce based on same IP and same cert. If you send an empty one, the connection basically says you can't coalesce at all, and it'll default back to what was in the SNI, which is the host name that's used in the TLS handshake. Or, alternatively, you can, in an origin frame, send a list of domains that are eligible for coalescing over this connection. And that list can change, so you can keep sending origin frames if you want to add or remove hosts from the list that you want. The origin frame is popular, it's been ratified, browsers are going to support it, and they give you basically the control back. Over coalescing. However, notice this little caveat. Actually, the wording is this. The wording is that the specification relaxes the requirement to check DNS when the origin frame is sent. Think about that for a second. That would basically mean that this wording is excusing the browser from doing a DNS lookup before sending a request on a brand new host name on a connection. That's interesting, right? That's interesting. However, just keep that in mind. And that's the first of, this is what's happening with H2, that's the first of a number of initiatives that are essentially making the connection a very authoritative and secure context for all communication between a client and server. For example, there's a spec for these things called secondary certificates, which is a way for the server to actually push certificates back to the client over a connection. If you think that the connection is this authoritative context between a client and a server, well, if I have a certificate for a host that I'm supposed to be authoritative for, why don't I give it to you? So there's a proposal for sending new certificates over the connection to the client. There's also, you may have heard about this one, DNS over HTTP, or DO. I'm not making that up. That is what they actually call it. So I bet you, I dare you to try to say it 3 times without Homer Simpsoning. So DNS over HTTPS essentially says we can do DNS queries over HTTPS. There'll be a frame, that'll be a DNS query, there'll be a frame, which will be a DNS response. What if we push DNS responses? That's going to be a thing. Lots of things happening over a single connection. So basically, keep your eyes on this, because there are initiatives to make this connection a very powerful thing between a client and a server. And it's scary on the one hand, but it's also kind of exciting because there's a lot of creativity that can come out of this. What if we can preemptively push DNS entries to a browser and bypass some late round trip time for when it comes to DNS? What if we can give and take away certificates to a browser and let it know more about who we're authoritative about? These are interesting things that are slightly mind-blowing, but they do provide interesting possibilities. So to sum up everything that we've talked about with TCP, the benefits, I mean, I think I can say jury's still out. I think there's enough use cases in the world to say HTTP2 is providing performance benefits. There's also anecdotal evidence that says it's not. Doesn't really matter, to be honest with you. We need to iterate on this core protocol, and it's okay. We need to learn these lessons and iterate and go forward. And HTTP 3, HTTP 2.1, whatever the next thing is going to benefit from everything that we learn. It seems like a new congestion avoidance algorithm is a good idea. This is BBR is the first step there. BBR v2 will be slightly better. There's other ways to address some of the problems. But again, collect data on your own and make these decisions on your own. And again, share that with the world. The community is very hungry for this data. We are getting more control over what we do with coalescing, and the connection itself is going to have lots and lots of new interesting things for us in the future. I'll take a breath. I'll take like 2 questions if you have any right now. Otherwise, I'm going to just plow through. Yeah.
Why is HTTP2 opt in on Fastly, not opt out?
Opt in, not opt out?
Yeah.
It's just the way it was easier for us to roll out. We wanted to see which customers wanted it.
Okay.
Yeah.
Any more? Oh. I told you not to sit on there. Yeah.
Hello, Andy.
What was number 4, Hooman?
Oh, I'll get to that at the end. That's in my future slide. Okay.
Hang on. One more.
Cliff. Oh, Cliff. Yeah, please.
Andy's question didn't count.
Please.
So everything you've shown so far has been synthetic testing. What did you find when you looked into your RUM data?
I don't have any RUM data. My customers do.
What did you find when you looked into your customers'
So
RUM data?
I would like to think that many customers are doing A/B testing. Unfortunately, not many have shared it. There have been use cases of people doing RUM testing. Actually, this guy right here, Patrick, before he was with Fastly, did a bunch of RUM testing where he showed at very, very high latencies, H2 was helping. Super high latencies, but it was not, do I remember right, Patrick? In low latencies, it was not. So again, there's some evidence of help and there's some evidence of, I don't know if there's evidence of hinder necessarily, or if people are seeing it hinder, they're not talking about it openly. But there is evidence, and you would expect that to be the case. I mean, there are things about the protocol that are beneficial. Now, I'm going to spend 12 minutes repeating what Patrick said 45 minutes ago. So, if you heard this stuff before, that's the guy to blame. I'm going to talk about server push, which is arguably the most, at the time, was the most exciting feature of HTTP2. Some basic things about push? The idea was to push a resource from a server to a browser before the browser requested it, before the client requested it. Only servers could push. It's a hop-by-hop attribute, which means if you have middle boxes, you can only push to the next middle box that you have. You can't push all the way through. Each box does its own thing. And one of those 10 original headers defined in 7540, push promise, is essentially used to trigger server push. Here's what the flow looks like. You have a connection. The request is made from the client to the server over, let's say in this case, stream ID 1. You ask for index.html. The response is first a push promise frame that is sent over stream number 1, but it promises stream number 2. And then after that, you send the data for index.html, and then you push at the same time the data for the CSS, for example, that you're trying to push. What this has done is this has eliminated the round trip that it'll take from the client to the server to request the CSS naturally as it parses through the HTML. So this is essentially a flow where a server can send content to a client before the client asks for it. The only pseudo rule is send the push promise frame before you send the content that references the thing you're trying to push. So in case of a CSS file, you want to send it before the HTML that's referencing the CSS file. Other than that, it's relatively, free flow. Use it as you see fit. When push was initially introduced, a lot of people saw it as a replacement for inlining. Remember when we take images and JavaScript and CSS and inline? This was seen as a replacement for it because we got all the RTT savings, and because we were pushing these resources to the browser preemptively, we also got the caching benefits. With inlining, we couldn't cache things on a browser. In this case, we can cache things on a browser. There was an open question of what to push. There's a Google paper on some studies that they did that said it's better to push this or better to push that. Facebook did an interesting talk on some creative stuff they did in your feed. And our own Patrick Hammond did a talk on time to first meaningful paint. That's the link for it, where he talked about some use cases for push. Now, how do you trigger a push? Well, it was sort of universally accepted that the best way to do it was to use a link header with the relation type preload. So link rel preload. And the idea was that you send this header on that index.html So a middle box or a proxy would know that it could push CSS1.css to a client. Who's heard of link rel preload, right? Okay, because link rel preload actually has an existing definition on browsers already. It's the way that you trigger a browser's preloader to load things into the browser without parsing through the HTML. So what the preload spec said was, okay, realize you may be using this to invoke the browser preloader. So we're going to add an attribute to no push attribute. So if you're a middle box and you see this link header, but the server, the origin server, doesn't want you to push the resource, if you see this attribute, don't push. That's great, except the spec didn't add the other side, which is what happens if you want the link header to only be a signal for push. So at Fastly, we added our own way. We just added a new attribute that was as many dashes as possible with an X in there to annoy as many people as we possibly can. And the idea was if we get this from an origin, we will only push and we'll rip this out and not send it to the browser. I have no idea if other CDNs have this mechanism. I would hope that they do. The reason we did it is we're big on letting our customers sort of experiment and figure out on their own what works for them. So instead of mandating specific things to them, we just gave them all the tools and let them decide. What are the benefits of push? Okay, let's look. Here are two waterfalls with and without push. In this case, the HTML, and this is important, in this case, the HTML is one round trip away from the client. This is an important distinction. In the situation where the HTML is one round trip away from the client, essentially what push gives you is a single round trip saving. Why is it one round trip saving? Because we designed HTTP2 to be multiplexing and interleaving. You can do all sorts of things at once. You can send all sorts of requests at once. You can send 100 requests at once from the client to the server. So in cases, again, where the HTML in standard HTML web browsing is one round trip away from the client, we get a one round trip savings when we push content. Now, I am a huge advocate for caching HTML at the edge, which is essentially how you make HTML one round trip away from the client. And I will talk to you until I'm blue in the face about ways to do this and why you should do this. However, there are situations where that's not possible, where the HTML content has to come from origin and there's no way around it because it's truly, truly, truly dynamic. That creates a situation that kind of looks like this. Now, in this situation, if I'm going to rely on a link header to come from the origin to signal me to push, look at all the wasted time in the network that I can't do anything. Because as a surrogate, as the middle tier, I have no idea what the thing is that I need to push because I'm still waiting for this header to come from origin. Enter early hints. This is now eradicated, now ratified as RFC 8297. It's essentially the introduction of a new status code, 103, which you heard Patrick talk about earlier. And essentially, the idea of a 103 is you can send some response headers from the server to the client before you send the remainder of the body that would carry the normal response header. So before you send the 200. So essentially, you can decouple that link header from the remaining response headers. This is what it looks like. So when the server sees the request for index.html, it can immediately send back a link header in a 103, which will trigger the middle tier to initiate push. And then the rest of the body can come whenever it comes and the server's done with its think time. However, this still gives us this much time that's wasted, right? It's better, but it's not the best. So as we learned about use cases, we decided, and when I say we, I'm talking about Fastly, but I think other CDNs also, I know of at least one other CDN that has this feature, a way to essentially trigger push without a header. Some sort of programmatic or configuration-based way to trigger push without a header. And this is essentially what the diagram would look like. When the request arrives at the CDN or the surrogate, you initiate server push and push the thing. And while you send asynchronously the request to the backend, let the server do whatever it needs to do. And when it comes back, it comes back. But by the time it comes back and the object is delivered to the client, we've done the push promise, and the client, we've pushed the content to the server, to the client, and the client has that content in it. I'm not saying in its cache, it just has it. This is a thing we called async push. Essentially, this was done through configuration. And if you know a priori what you want to push on specific content, you can essentially trigger this through configuration. Our configuration looks like this. We use VCL. This is very simple to essentially initiate server push this way. What's cool when you do this is your waterfalls look amazing. Now, this is an exaggerated waterfall. I did this on purpose because I wanted to show the benefit of this. So what happens when you have huge server think time is you have this dead white space, nothing happening on the network. When you use async push, you essentially get content to the browser very quickly. Notice how those 4 objects down there are essentially hiding under the server think time. This is taking advantage of that big white area on the waterfall and getting content to the browser. Now, that's cool. This is a good use case for server push. This is arguably the only good use case for server push when it comes to web content. But as it turns out, it is not that simple because there's a thing called a client cache. And the protocol has no provision for what to do if this thing that you're pushing is already in the client cache. This is the only provision it has. There is a notion that if the client has the object in its cache, it can reject the push with a frame called a reset stream. But this is what the time chart looks like. Here's the request. Here's the server sending the push promise. And by the time the client gets the push promise, the content is now being pushed. And that's only the time that the client can actually reject it. So by the time the client rejects it, the content is already in flight. This is not ideal, to say the least. So even the provision that is put into the protocol to essentially cancel a push is flawed. What's worse is this. Look at this waterfall. This is a first view and second view waterfall with no push. It's just a bunch of images and some CSS. The only thing that's dynamic in this case is the HTML. That's the only reason you go back to the server. I'm a good performance citizen, so I put good cache control headers, all my content. When I go back to the server for repeat view, all I fetch is the HTML. This is what you expect to see in a first view repeat view case. Look what happens with push. If I push 4 things to the client upon first view, the client comes back and does a repeat view, I'll push those things again. Even though I would expect under any sane circumstance for those things to be in the client's cache. Why is this happening? Well, it's complicated. There's a blog post that Patrick was talking about earlier. Yoav Weiss wrote this excellent blog post with very nice pictures from his daughter. She drew them, which explains that caching in a browser is actually quite complicated. There's multiple caches. There's an HTTP object cache. There's a push cache. That's a different thing than the object cache. When you push, you put it in the push cache, not in the object cache. There is a memory cache. There is a service cache. There's all sorts of little storage areas that a browser has for caching. So there's a huge complication here that basically renders push suboptimal. Even in the best case scenario, when you have a large server think time, you may push things to a browser that it already has in its cache. So of course, what do? We add new features. There is a notion, there's a spec called a cache digest that's out there as a proposal, which is a new frame, which will be sent from the client to the server. And a cache digest essentially is a way for the client to tell the server what's in his cache. You send this frame during the communication duration of communication, and this will inform the server what to serve or what to push when it needs to send you push content. It's an interesting proposal, and it does sort of solve the problem of what's in the browser's cache. This is all to show you and to say that we still have a lot of work to do. And nothing proves this better than this great blog post from Jake Archibald, a London native, if I remember right, about why push is just rough. Northerner. He's a northerner. Again, Patrick just has all the information. It's a great blog post. It really outlines all the reasons push is complicated and why it's difficult. And again, remember, all of this is for most of the time, if your HTML is 1 round trip away from the client, it's 1 round trip saving, 1 RTT saving. There is a use case that we have, which we like, which is when the server has large server think time. Okay, what's the adoption of push like? Okay, again, we can do a survey, but I'm going to go to the network and show you what my caches showed me. So here's what I did. I went to some Fastly caches and I looked at 30,000 HTTP2 requests. Out of these 30,000 requests, guess how many of them were pushed? No, I was looking at other people's traffic. I wasn't doing my own. 10 out of 30,000. 0. That's ridiculous. But it's close. So very low adoption. And I will tell you this, that when I did this 2 months ago, the numbers were half of this. That's a server in US East. I also looked at US West, slightly more popular. So, we go from 0.003% to 0.004%, I believe. And what about the civilized world? Well, somewhat similar. This was just earlier today. So there is some adoption, but it's not like hugely used in the world. While we consider this push world that we're talking about, let's consider this. Remember this use case, which is we agreed, well, by we agreed is I agreed and then told you, that this is basically the best use case for standard web push. Well, remember that 103 response that I was telling you about, the 103 status code? What if it comes from here? And essentially, while there's all this thing time, this white space between the client and the server, what if the server sent the 103 directly to the client, and it gives the client all this time to do all this fetching? That essentially gives you the same benefit. In fact, the 103 draft talks about this and says that there's a problem with push that essentially makes it suboptimal if stuff is already in the browser cache. It would still give us the same waterfall, and it's that little time up front where the 103 comes. So we still essentially get the same benefits with far less complexity. And because 103 is using a link header, which we already know how to use in a browser, we also take advantage of the fact that if something is in the cache, we won't put that request on the wire. There's no wasted bytes on the network. This is gaining some steam. One of the reasons Patrick said earlier that push is sort of iffy right now is because this seems to be solving the major use case problem, and it's significantly simpler, much less scaffolding necessary for this. So the questions we need to ask is all that scaffolding and all that complexity necessary for that one RTT benefit, where we can basically get the same essential benefit from a 103 for the most important use case, and it's much simpler? Are cache digest still helpful? Will they still serve us a benefit? It seems like it's a good idea for us to know what's in a browser cache. Maybe push isn't the use case, but maybe that's a good thing to know still. And then there's an open question of what do we do with push? Do we rip it out? My personal opinion is that, and I thought of this, I think I may have subconsciously thought this all along. There's probably use cases for push that we haven't thought about yet, that have nothing to do with web browsing, that are unique and have to do with two-way communication. There are plenty of situations. HTTP general is a one-way, client and a server. There's going to be things that we want to have the server sent to the client or initiate to the client. There's probably use cases that we haven't thought about yet where push is going to be beneficial. And I think some of the hesitance that we'll feel about from browsers yanking this out altogether, which I don't think they're doing anytime soon, I may be wrong, is there's probably use cases that we just haven't thought about yet. And that Facebook video that I showed you earlier is a good example of that. That is a creative way that's not really traditional webby. That's a good way to use push. Okay, that was push. I'm going to keep going because we have 2 more features to go through. We have prioritization. I'm sorry I misspelled this, but back where I come from, it's a Z. So prioritization is arguably the least understood. I'll take that back. It's the least leveraged feature in H2. It's a powerful feature, but I don't think anybody's actually doing anything with it. What is it? Prioritization is essentially the idea that when you've created this connection that is multiplexed and interleaved, and you have a lot of concurrency going on, there's going to be contention. How do you prioritize? How do you figure out what to do first? So prioritization in HTTP2 tries to solve this problem. Solve this through 2 mechanisms. One is a weight of a server, which is of a stream, which is essentially its priority. And then the second is dependency. One stream can be dependent on the other. And that could be an exclusive dependency or a non-exclusive dependency. Priority is dictated from the client to the server through either a headers frame when you set up a stream, or through a separate priority frame if you choose to change the priority of a stream. This is why a priority frame is one of the 10 that was originally designed. And it's only a suggestion. So it's just a way for the client to say, hey, I'm telling you that I think this one's going to be more important than the other one, and the server is kind of free to do whatever it wants with it. Some examples, again, these are from Ilya's book because they're good examples. There's no reason to come up with new ones when somebody already has good ones. Here are two streams, A and B, and their weights are, let's say, 12 and 4. What this means is, hey, server, from all your resources, take 3/4 of it and give it to A, and take 1/4 and give it to B. That's the ratio between those weights. If you have a priority tree like this, you say basically take all your resources and give it to D, and after that's done, give all your resources to C. The weights in this case don't actually matter because there's no contention between sister streams. Here's a more complicated one. In this case, you give all your resources to D, then everything to C, and after C is done, you again do that 3/4 and 1/4 to A and B. And here's the most complicated one: is you give all the server, you give all your resources to D. After D is done, you give equal resources to E and C. E does its own thing, and after C is done, you give whatever's that half was that you gave to C and divide it again, 75% and 25% to A and B. So what you'll notice here is that these trees of dependencies are being built between a client and a server. What gets really interesting is how these trees look like in our clients. So check this out. This is the way Firefox builds the prioritization tree. It actually starts with 6 streams if you count 0, but 5 streams that essentially are roots or nodes in a tree, and the streams themselves aren't used. They're like ghost streams. And then a tree is built underneath those with dependencies. I don't know why this was chosen, but it certainly has the feel that many smart data scientisty people sat and decided that this was the best thing to do. That's cool. Edge is slightly different. It has, well, it's just flat with no priorities and no dependencies. It's just everything's the same. The stream numbers are different, so yay. Safari is also slightly different. Again, no dependencies and there's no dependencies, but there are priorities based on the type of content that you fetch. And Chrome used to look like this, where you have weights, you have priorities, but you don't have any dependencies. Chrome's tree about 1.5 years ago changed. So if I show you the tree of that page that's got 100 objects on it, it kind of looks like this. Actually, it doesn't look like this. It looks like this. So the way we map this out is Fred on the Fastly team built a little tool. There's the link to it right there. That essentially you take the net internals output for an H2 stream, shove it into this tool, and it gives you a little picture of how things look. And if you notice something very interesting in this diagram, this tree, is every image is dependent exclusively on the image before it. This has basically built an exclusively straight tree down. So it's not really a tree, it's a bark, right? The only reason there's 2 in this case is because one just got done. It was just a timing thing. This is essentially taking away interleaving from H2, which is really interesting because this is essentially anti-feature. There's an open bug about this. And there's a lot of, this is only the top of it. There's a lot of interesting discussion down below. If you're interested, check this out. Last I checked, Chrome continues with this strategy. I'm sure they have a good reason for it, but it does create essentially a situation where at least with these 100 images, maybe it's different when CSS and JavaScript and complexities enter the picture, you essentially have exclusivity throughout everything that you're fetching. What's happening with priorities today? Well, there's these initiatives to essentially give some of the prioritization control to the coders. There's 2 initiatives that I know of. That's essentially ways to manually declare priorities programmatically, I suppose, on the client side. There's something called priority hints, which I imagine is a way to essentially declare them as you would with anything else that you fetch from a browser. I don't know if these have a lot of steam right now, but it would be a natural progression for this feature to give some of the flexibility and some of the control back to the users who are programming the sites. The last feature I'm going to talk about is HPACK. I was actually going to rip this out because this is a little too weedy, as in I'm going into the weeds a little bit too much. But Patrick Hammond convinced me to keep it in because there's some interesting information in here. So if you don't like the next bit, you can blame him. Everything else, you can blame me. Just this part, you can blame him. HPACK was defined in its own RFC. It's a companion RFC to 7540 and 7541. It addressed the header bloat problem. The finger quotes were not around header, it was around bloat. I may have done them out of time. And essentially has two primary mechanisms. One, every header name value field is Huffman encoded, and there are index tables on both sides. Essentially what HPACK does is instead of sending full headers, you send a pointer or an index to a header across. So it's not, I guess it's called compression technically because you send less bytes, but it's essentially an indexing mechanism. There's two tables. One table is called the static table. The static table is defined in 7541. It looks like this. It is defined as to never be able to change. You can never change it. It's like this. It's hard-coded. Clients and servers ship H2 with this table built in. It's essentially a list of all the popular headers and some of their values. And then there's a dynamic table. That dynamic table is built dynamically during the lifetime of a connection between the client and the server. Each side maintains its own, and it's a FIFO table, which means if headers enter the table here and other headers come in later, this header's index falls. So let's say a user agent goes in at index 62 and other headers keep showing up. That's the same name value pair is going to go to 63, 64, 65. It's going to keep going. This is weird when I first saw it, but that's by design. Is there a performance benefit? Well, I think intuitively we know what the benefit is, but it kind of helped for me to visualize it. Here's the bytes sent from a browser to a server, so request flow. When HPACK is used in the blue line with H2 and when it's not in the orange line with H1. This makes sense because most of what we send from a client to server is requests and their headers. So you make all the headers be indexes or indices, and you reduce bytes significantly. And again, I probably inherently knew it, but it was interesting to see it in a picture that the number of bytes that are saved from the server to the client are not significant because most of what's coming from the server to a client is body bytes and is payload. And a very small percentage of it is actually headers. This is essentially what the study by Dropbox also pointed to. You see that in this case, their ingress traffic dropped by a lot, which is request volume coming in, but their egress didn't really change all that much. What should you know about HPACK? Well, the first thing you should know is by the spec, the default dynamic table size is 4K. That's in bytes. That's for the entire dynamic table. This is the content security policy header from Twitter. You know how big this is? That big. Which, under default circumstances, would essentially, if the browser and the server chose to index this, or if the server chose to index it, it would essentially overflow the table immediately. That's one thing to remember. I'll tell you why this is not that big an issue in a second, but it's a thing that we should know. There is a way to mitigate this. There's a somewhat, I feel like it's somewhat abandoned, I'm not sure. There was a proposal to do essentially site-wide headers. So headers that you would do for the entire site rather than send things over and over again. We got to remember that compression context is per connection. So the whole notion of when you shard, if you were to shard with H2, that would essentially create multiple compression contexts. Can't turn it off. It's not an optional feature, although you can choose what you index and what you can't. And there's a paper from Imperva which actually shows you how it can also be an attack vector. Now, 2 years ago when I looked at this, browsers essentially kept the table sizes at default. I'm happy to say that browsers are now increasing the table sizes. But one of the most important things that I learned recently isn't the fact that the table sizes, the dynamic table size is bigger, is that there aren't actually two dynamic tables. There aren't actually two tables. There's actually three tables. And this is the way it works. You have a static table on both sides. So when the client and the server come up, they build, they initialize with a static table. And the spec says that through a settings header table side frame, each side can tell the other side how big a dynamic table it can hold. The key here is that it's the decoder who's dictating the size. So in that header, in that packet, in that frame, or in that setting that's coming from the client to the server, it's the client telling the server how big its decoder is going to be. And there's an equivalent setting from the server to the client, which is the server saying how big its decoder table is going to be. Basically what this means is each side has two different dynamic tables, and what's in that table is the minimum of what the that side is declared to be its decoding table and what the sender decides to essentially make the size of its own table. I think I said that right. The idea is that there are two different dynamic tables, one used for decoding and one used for encoding. What's the biggest takeaway? I asked Patrick, why do you want me to keep this section in? It's so boring. He said, the thing to remember with HPACK, wise people always have wise things to say at the end, is that it is not the be-all, end-all. It is not the thing that solves all our problems when it comes to large headers. There are lots of situations when it doesn't necessarily solve the problems. So really, the only reason I have this in there is to just make you aware of issues with it. And if you ever come across it, if you're using it, if you're like Andy and I, using Wireshark, looking at indexes flowing over the wire, be aware of how things are being indexed and how they're being used on each side. I'm going to finish up with two things. Very quickly, I'm going to go through some tools and some resources for you to do further studying in this if you wish. I know I've just inundated you with data for the last hour. Here's some more. Read this book if you haven't read it yet. Ilya added a chapter on H2 specifically to this. It's a very good chapter. It's only like 20 pages or so, but it's a very good overview of everything H2. There's a little browser extension that tells you if you're using H2 or not. I can no longer go to a website and my eyes always just go to the little lightning bolt to see if it's H2 or not. You know what I'm talking about. H2 is now exposed very well in DevTools in both Chrome and Firefox. You know if you're speaking to a browser, to a server through H2, through DevTools. And my favorite tool of all, Wireshark, lets you look at the actual frames going over the wire. What's the catch here is because it's SSL, TLS, you need some way of decoding that. And that post right down there shows you how to do it. There's a way to create a pointer in your machine to a file where all the keys are basically written, and you point Wireshark to it as well. And then Wireshark can decode H2, and you can see cool H2 things, right, Andy? It's great. Or you can use WebPages that gives you both the, right. It'll give you both the capture and the key log, the key file, the key log. Curl has supported H2 for quite some time, but the best news is that just recently, Curl also shipped the ability to write the key file, to write the keys to the same key file. So now you can watch Curl with Wireshark over the wire, which is, I know you're all excited about it. I can see it in your eyes. This was a very big deal for me because I could finally see things on the wire. There's a curl-like tool called NGHTTP that actually gives you a breakdown of all the frames that are going over the network when it comes to H2. There's some other things for more troubleshooting. Has the world gotten better at tools since a year and a half ago? Maybe a little bit. I don't know if I said, but curl now can be decoded with Wireshark. That's a big win. Okay, let me finish the day, this rant of mine, with what's happening next. It is hard to argue against the fact that HTTP got quite complex from 1.1 to 2. If you look, this is relatively an accurate depiction of its complexity. Now, some people in this room, probably those people sitting in the back, maybe this guy taking a picture, will say that I feel this way because this resembles a different graph. It's possible that I've become a curmudgeon and I just think things are getting complicated. But it is hard to argue that things are actually complicated. Now, if you think this H2 was complicated, you ain't seen nothing yet, because the next thing is this, is Hvac. Hvac is the new cool kid in town. It's what everybody's talking about. H2 is yesterday's news anymore. And it's got its own logo, actually. Isn't that cool? And this is what we talked about when we had that panel a month and a half ago. If you take one thing away from this presentation at all, other than Patrick is going to talk about your presentation during somebody else's presentation before you give it, other than that, if you're going to take one thing away, is that we did this thing with H2 where we didn't call H2 Speedy. Remember Speedy, the Google protocol? When Speedy became the premise for H2, we didn't keep calling it Speedy. We called it H2. So there's no confusion anywhere about what's Speedy and what's H2. We know exactly what's going on. We didn't learn that lesson when it came to Hvac. So Hvac actually means two different things. And it's important to be to have the distinction. One, and this is what the community started calling it, It's Gquick and one is iQuick. Gquick is the Google thing. It's the protocol that's Google proprietary. It's monolithic, and it's basically on Chrome. It's unlikely that any other browser is going to have it, and it's very Google specific. iQuick is the effort to standardize, to use Gquick as the basis of standardization for a open protocol that's modularized, and that's the one that has the logo, so that's going to be the cool one. That's going to be what the efforts of the IETF are going to produce to us when we have a shipping version of Quick. It's going to be iQuick. The stacks kind of look similar, but they're kind of different. There was, again, a lot of proprietary stuff with Gquick. iQuick is going to leverage TLS 1.3 rather than the proprietary Quick Crypto. It is a transport protocol. It is a complicated protocol. It's actually one of the reasons that adoption is going to be rather slow, because a lot of people are considering it a wholesale replacement for TCP. One of the things that Quick gives us is the ability to do all the congestion stuff, not in the kernel where it's really difficult to iterate, but in user space, in code. And that's a big benefit for us when we try to iterate on the internet. These days, iteration is king. It's not one spec, it's 4 specs. There's a way to map HTTP over Quick. There is a congestion algorithm for Quick. There is the standard TLS side of Quick. And there is, what else is there? Just the standard UDP definition of Quick itself. So it is it will be a complicated protocol. So, if you're this far, you've sat through this whole thing, you obviously like complication. So you're going to like Quick. Here's what it's promising us. It's promising us low latency setup time. So it's going to be leveraging TLS 1.3 zero round trip, 0 RTT, which means if you've been to a site before, you don't need to do a handshake. You can essentially send data right away. It will be based on UDP, which will address our TCP header line blocking issue. Because the congestion algorithm is going to be in user space, it's going to be more flexible, easier to iterate. It'll promise us rich signaling for congestion and loss recovery. Everything's going to be encrypted and authenticated. This basically bypasses any silliness that's happening in middle boxes. And it has a very big feature, which is connection migration and what they call Nat Rebinding. The idea here is I have Quick, I'm in my home on my browser, on my Wi-Fi, and I leave and I go get in my car and I'm 4G. I maintain my connection to the server through what's called rebinding. This is done through a connection ID that's established between the client and the server. Here's a bunch of reading. If you want to learn more about Quick, there's things you can learn from these readings. Again, very academic things, and a good little video there that'll talk about the basics of Quick. As we hit slide number 190, you're welcome, we can ask how much has changed. So have things changed since a year and a half ago? Yeah, kind of. I think what we're seeing is we're learning. Is what we're learning being fed back into the machine? Kind of. I think, as we expose more data, we talk about this stuff more, I think we learn. I think what's happening in Quick is, and its standardization efforts is an indication that we've learned some things that we want the next thing to happen relatively quickly. We do still have a lot to learn, I think. We still have a lot to do. Again, I always talk about this. All of us have a responsibility to release data to the world. If you do tests, if you have data, if you have information that informs the community about how these protocols can be developed further, tell the world about it. We are hungry, all of the community. I'm not one of the Illuminati that's writing specs, but we all want to know about this data, and we all want to learn and iterate positively. And whether Quick will fix everything or not is still to be determined. My 191st slide is this. I think we have some time for questions. I went at a breakneck speed, I don't know, it was fast. We did it in 1 hour and 10 minutes, so I'm proud of you. I only saw 2 people asleep, so that's actually much better than I expected. Can I take some questions until you shut me down?
Sure. Yeah. About 2 years ago, I saw a fantastic presentation about how with JPEGs you can make them progressive, and then you can only send the first 10%. And I thought with the prioritization feature that you could actually only send that first 10% first, so you can already see a blurry image with already some image. and then it would then later on get it. Is that actually possible with H2?
Not with prioritization per se, because I mean, technically it's possible because you would be changing the priority of a stream midstream. I think that's possible. I think the feature that would enable that more is the ability to be able to send, if it's a progressive image, the ability to send chunks of the data before others. This is the interleaving part of H2, right? So I can send the first couple of passes, so you see the blurry image, and then send data from other images or other requests, and then send the rest of it sort of later. I think that's a way that you could do it. I think one of the early like push features was, can I push the first 2 passes to you and then maybe push the rest of it to you later? I have yet to see this in practice. So I think on paper, by spec, I think it's all doable. I don't know of anybody that's actually doing it. So I think theoretically it is, but I'm not really sure if it's in practice. I don't know. They're just opting in.
I was going to say, how fast is Fastly rolling out new features? I mean, obviously the HTTP2 took a while. I was waiting for it for a while. So like the newer features as they come on board, how fast is Fastly iterating and deploying them?
You have an example so I can get something like give you
just in general, like do you have a roadmap in place to roll these features out?
Yeah, so I think we rolled out async push before anybody that I know of, and I may be wrong about this, but it was relatively early. We are rolling out features. The benefit of where Fastly is sitting right now is we have a number of people that are in the core authorship of these things sitting at Fastly. So the quick author is part of Fastly. The person who wrote H2O is part of Fastly, who's working on HTTP2. BBR author is part of Fastly. The co-chair of the HTTP working group is part of Fastly. So there is momentum inside the company. Anything that's standards-based is we're all advocates of standard stuff. I'm not sure if you're ever going to see G-Quick from Fastly. I don't think that, I'm not in a position to say if you are or aren't, but we're huge iQuick fans. And we're trying to push iQuick as much as we can. Not necessarily by just hiring all the people, but because we're a fan, we see huge benefits. It fits into our network well. I'm sure every CDN is going to tell you this, by the way. It is a thing that we're all as a community looking forward to. We're going to roll it out as quickly and safely as we can for our customers. And that's the best I can do. We're gonna do it faster than you would expect. Now, this means I will probably disappoint you at some point in the future. That's okay. But we're big advocates of some of these big ones. The origin frame's already in the works. There's other things that I can't tell you about that are in the works, but there are things that we want to, we're advocates of everything standard-based. We're big fans of.
Any more? Oh,
Andy, make it
good.
good.
Make it good. So we'll call this the last one.
Have you persuaded Patrick on the benefits of Wireshark?
This
yet?
Patrick.
That Patrick, yes.
Oh, Patrick, have you been persuaded of the benefits of Wireshark? Sure, he's got a nickname for it. I'm still working on it.
Hooman has enlightened me in the ways of the shark, yes.
Oh, look at that. Anything else? He's fine.
Yeah,
Thank you, everyone.
Anyway,
Thank you very much.
yes,
Thanks for staying.
please, big round of applause for Hooman.